In the previous video, I took our original simple linear bar, axial stress and strain, and using a more appropriate constraint on the model than we started with, I actually was able to drill a hole in that model and see that it made a significant change in what we predicted. So let's look at that a bit more. Here we are back to the solution that I showed in the previous video. Now, a couple of things are interesting to note here. One is if I look at, say, the strain, you can see that the necking down of one face of this model seems to be on one side. And is that because I applied my new boundary condition, which was appropriate for the model that I was looking at originally, which was a simple model, and yet I've got one side is very much distorted, and one side is flat. So we can once again look back at these fixtures and say, well, maybe those weren't quite what I wanted. Maybe what I've done is I've once again, with the boundary conditions, created an unrealistic simulation model. So maybe I should be going back to my earlier model, which had simply a rigid constraint at the top. And maybe I should consider that as being a better simulation, more realistic to what I'm looking for. So it looks like we've gotten into a bit of a problem where by adding a very small detail feature like a hole, we've actually found that the boundary condition that worked for the simple model doesn't work anymore. So as with any time when you're finite element modeling, you have to look at all of the features with each of the models that you create. So you can't just say, I'm going to use a particular boundary condition and leave it at that. The boundary conditions you use need to be consistent with the purposes of your model and the level of detail you want in the model. The mesh that you use has to be appropriate for the level of detail that's in the part that you're simulating. So you really have to be very, very conscious of those fundamental elements of the boundary conditions, the mesh, and the loading and the results. So you really have to pay attention. This isn't just a plug and chug kind of tool. This is a tool that you can use well or you can use poorly. So let's try playing with some more features here and see if we can make this model more reliable. I've tried making models now with a fixed face at the top, and I found that that was problematic because it didn't really reflect reality. I tried a model with 3 planes as roller supports, and I found that that too made an unrealistic model result. Now, you wouldn't know that just by looking at the number that was calculated for the total deflection. You have to look at the details of the simulation and look in particular where you should expect to see features that make sense. For instance, in the area around the hole that I created, the hole was in the middle, so there's no reason to expect that the result would not be symmetrical about the hole. So what this is telling me is that whether it's the solution in this case with the fixed plane at the top, which I've done by meshing it around, and this is a very coarse mesh, or whether it's the same problem, but this time using 3 planes as the fixtures, as roller supports, both of these solutions give me a result that wasn't really making sense. In the case of this one, we have it a symmetrical geometry, and yet two of the planes, which I'd attach the supports to, are basically flat, and all of the plasticity, all the strain is happening on the opposite face. So that doesn't seem right either. And I can play around with the mesh. In this case, this example showed a much finer mesh, but still you can mesh it as finely as you like and take all the computing time that you like. But if the fundamentals of the model um, boundary conditions are not correct with respect to what you're trying to model, it doesn't matter. The answer will still be wrong. Just like if you've got the correct boundary conditions and yet the mesh is too coarse, then the answer will be wrong. All of these things have to be appropriate and correct for each other in the conditions. So I've created another scenario. Now this one, I've instead of using the planes as my boundary conditions, I've chosen another boundary condition. In this case, I've chosen a cylindrical face. So I've picked the cylindrical face of the hole that we've created, and I've locked it in translation in axial and crosswise and rotation. So basically, I've made this a rigid pin bearing to support the whole bar. Now that's quite a different constraint, and it should give us a different result. In terms of the mesh that I'm creating, I'm going to make a fairly coarse mesh. I'll go with the 7.5 millimeter mesh. I'll use a bit more of an advanced construction for it. And I create the new mesh. And let's see if we can run this result. Now, if we look at the stress on this, that's kind of interesting. All of the stress up here, where the bar is essentially not being loaded by anything, is zero. And there's quite a bit of stress around the bearing surface of the hole. And that makes sense. We would think that if this is being pulled, that we should see a high compressive stress at this point, and we should see a tensile stress at this point. And not sure at this yet if that's the case. If I look at the strain, then the strain plot shows that yes, I'm straining this quite dramatically, but up here not so much. Now that makes sense in the sense that if what I had done was specified that this was a rigid pin going through the part, then the pin is round and is going to stay round. So if the pin is round, then the material that it's in contact with will stay that same shape. And in this case, that will stay undeformed circular. So what we will expect to see is all of the change of the hole shape would be down at the bottom here. And that sort of makes sense. Let's look at the stress again. And we're also seeing in this model the necking down is consistent in the opposite sides of the part. So this starts to make more sense as a realistic simulation of a part if we were actually making something that was a straight bar with a bolt or a pin holding it on one end, being pulled by a distributed force at the opposite end. Now, the proper thing we should be doing with this is doing a series of runs with different grid sizes, grid geometries, with different hole sizes, hole locations, to just get a sense as to whether or not our model is behaving as one would expect from common sense, and whenever trying to find the validity of the model to try and take it back to a hand calculation that you're confident in. But we're not done yet, because recall that what I said was the pin that we used as the boundary condition looked like it was keeping the hole round, which you could imagine it would. But let's look again at this detailed picture, and looking up close, looking at the stress is interesting. Keep in mind that if you look at the grid or the mesh, that we're really meshing this in such a way that there aren't very many finite elements around the hole. So that means that looking at this stress plot, that a lot of the detail in here is smaller than the size of the finite elements that were used to solve the problem, which makes me skeptical that it's realistic, because it's really showing features that are smaller than it has any right to be claiming. So before we make any conclusion about what's going on here, we really need to look more carefully at the size and the design of this mesh that we've got. So let's go back to going to our mesh. In this case, what I'm selecting now is I've got a very large maximum element size, and I've got a very small minimum element size for the mesh. I'd like to have around any circles a much larger number of elements. I'm going to go as much as 15, let's say. And I want to maybe grow these elements much more rapidly. And let's see, by changing those parameters, what I get for a new mesh. So you can see now with this mesh, I've got coarse bits here where nothing much exciting is happening. We know that already. And yet I've got relatively fine points here around the hole where something interesting is happening. Now maybe I can do better than that, and I can reduce the size of the minimum mesh piece even smaller still, and increase the number of elements around a circle, and see what that gives me. So now I've got a very fine mesh around the actual circle. I'm not very happy about how coarse these are, but I'm willing to give it a go, and we'll see what we can get. So let's see if this will run. So now we've got, looking at the strain, now we've got a simulation that shows a lot more detail of the strain around this hole. Looking at the stress, looking at the stress plot, you can see that also the resolution of the stress is much finer. The details of where the necking down occurs is interesting. That's changed in where it happens from what we saw before. And in general, we've gotten more refinement around this hole. Now, I haven't been looking at the magnitude of the total deformation as a check, but that's something you'd want to do just to see how much that change made in the total result. But certainly looking at the details, you could just on face value look at that and see that that is a bit more similar to what one would expect around a hole if the pin is supporting it. And so I'm feeling more comfortable with that with that approach to the model. I'm not totally convinced yet that this is correct, but I think it's going in the right direction. So where are we now? Well, we've played around with the mesh, certainly. In this example, we just tried making a more adaptive mesh that was fine around the detailed features and coarse around the boring bits of the model. And that's a good approach because you only have so much computing horsepower. And in fact, you can't have an infinite number of points to get a reasonable solution in a reasonable time. Um, so you want to put the fine uh, components of your mesh close to where there's something interesting happening in terms of a change of stress. So that's what we did here. So we played around with the mesh, and that made a difference in the solution that we got. Likewise, we played around with really making a more realistic boundary condition. So we originally started with just simply nailing the top plane of this bar to the wall or the floor. And we found that that created some stresses that didn't seem realistic. So then we went back to a much simpler geometrical sort of boundary condition that set the planar boundaries. But then we found when we looked at more intricate details that that wasn't doing a good job of reflecting what we'd intended in terms of the support. So we had to go a step further still and really think about the realistic part we were talking about creating and how it really is supported, not just using the simplest possible approach, but coming up with an approach that actually reflects what the part was doing in real life. So I hope that you'll see that rather than just taking your CAD model and simply running a simulation with all the default settings, we need to start looking at what those settings really mean because they can have a big difference on whether or not you've created a model that is just pretty colored pictures or something that's worthwhile and gives you useful information. Thanks for watching.